Hello and welcome to Calculus Tutorial. We have one big topic left to look at, and that is volume. As you can see, it's a big one. We won't do all of this right now, but we'll do two of these boxes here. So volume, we're going to take our two dimensions and extend it into three. And there's two main methods here, the disk method and the washer method, and then many ways to rotate our functions. And so that's what we're going to do. We're going to take our graphs and rotate them to make three-dimensional shapes. And then we're going to find the volume of those three-dimensional shapes. So we're going to start with the disk method, and we'll see how that can help us find the volume. So first, let's just take a quick look at what this actually is. So here we have a function. It's a part of a sine function. And so what we're going to do is rotate this around the x-axis, and then that is going to give us a three-dimensional shape. So here's what that looks like. Around it goes until it makes a three-dimensional shape. So let me give you a look-see here. You can kind of see the three-dimensional vase that it makes. Let's watch it go around one more time. So there's the function, and then it rotates around the x-axis to make a three-dimensional shape. And we are going to be finding the volume of that shape. So how are we going to do that? Well, I got another picture for you to look at. Oops, that is not the one I wanted. This is the one I wanted. So if we have a function, so here you can see a function there, the way we're going to find the volume is by stacking cylinders underneath it. You can see that makes the little rotated circle shape like we were seeing in the previous ones. So if we're going to be adding up all this volume, all these cylinders, the integral is what's going to do that for us. The integral added up rectangles before. Now we're going to use the integral to add up cylinders. The nice thing is we never actually have to add those cylinders. The integral and the calculus are going to do it for us. So the volume of a cylinder is pi r squared times height. But obviously all we have is this function. I think this one is a square root function here. So how do we go from the function to pi r squared times height? Well, take a look at these cylinders. We've got the circle there. And what might help us visualize this is where is the x and y axis. So here's your y axis, somewhere in here. And then here is your x-axis going through the center of all of these cylinders. So if we need the radius, that will be the distance from here to here. Or for a bigger cylinder, from here to here. Actually, I'm going to draw that in a slightly different place. The better place to see it is from here to here, and then the largest cylinder from here to there. So what is that distance? Well, that is simply the y value of the function. The distance from the x-axis to the function is simply the y value. And so our radius is just the y value of the function, f at x. Now what about the height? Well, the height of the cylinder is down here. All of these, which is simply from here to here. That is the change in x. All right, if I add more cylinders, that change gets smaller, of course. All right, as you can see, this distance is now smaller. But another way of thinking about change in x is dx. And that change is, of course, going to go down to 0 as we add more and more cylinders. So our volume formula becomes pi times f of x squared dx. And then to add them all up, we take the integral. And so that becomes our volume formula right there. I'm hoping you can still see that it is pi r squared times height, the same volume formula for a cylinder, but now we're using an integral to add up an infinite number of them. All right, so let's use that idea in an actual problem or two so we can see how it works. So let's go back to our PowerPoint here. So first we're going to revolve around the x-axis. That's the easiest thing to do. So we've got our equation, 16 minus x squared, and we're going to revolve it around the x-axis. So first we're going to draw this region that they're talking about. And if you don't know what that graph looks like, you can graph it on your calculator, but I've seen it many times. It looks like that. So the region is bound by the curve f of x, so this is one boundary, and the x-axis, so this is the other boundary. So this area right here is our region, and we're going to rotate that around the x-axis. So let me put this in a different color. It will eventually come down here and be a mirror image. Not super important there, but our cylinders then would look like this, from there to there, and then down a little bit. So that would be one cylinder. Now that's kind of hard to visualize, this huge three-dimensional shape. What's important to know is that that circle is going to give you your radius. And so you don't even have to worry about the bottom. You just have to know that the rotation axis is the middle of your circle and the function is the top. Okay, you only really have to worry about that half circle, because the main thing we need is the radius. So what is the radius of that circle? It will be from there to there, which is just the y value of the function. So our radius is f of x. So when we do our volume formula, it will be pi times the radius squared dx. And our radius is f of x. Now we also have to figure out what our limits are, from where to where. Well, our region starts there and ends there. So where are those 2 points? In this graph, that will be at -4 and 4, because both of those numbers make our function equal to 0, and that's where the boundary ends. So this will be from -4 to 4. So that is the integral that will give us this volume. And most of these you're not going to do by hand. You'll do them on the calculator. So I'd recommend just making sure you can practice putting all of this on the calculator. So we want the integral from -4 to 4 of pi times, now I don't have f plugged into my calculator, so I actually have to type it in as 16 minus x squared. And then that is squared again, because the 16 minus x squared goes in here. Now one important note, if you see the pi times the parentheses, you do need that multiplication sign in the calculator. It doesn't recognize the multiplication when you just put the pi next to the parentheses. Yes, I know when you write it, that's all good in the hood, but for some reason the calculator does not like the pi just next to the parentheses. It'll give you an error otherwise. So one little thing to remember. And we hit enter, and we get 3,431.46456. So that is our answer. Volume is usually fairly large. It's three-dimensional. The numbers get big pretty fast. All right, so that is revolving around the x-axis. That's about as easy as it gets. I want to do one slightly harder type of revolution. All right, so we did the disk method revolving around the x-axis. We're going to do one now that's just a horizontal axis of any type. So not the x-axis necessarily, but a different horizontal axis. So here we have our region R, and we're going to revolve it around this blue dashed line. So it will come down here, and then our cross section will look something like this. So what is the radius of that circle? That is our big question. That's always going to be the first thing you want to find. What is the radius? Well, that distance, we don't have a function for that distance. Our y value is from the top dot all the way to the bottom. Okay? And that is not the radius. I just need this little bit. So how do I get that? Well, I have to take that large y value, f of x, and subtract off this bottom piece, which is not part of the radius. Well, how tall is that bottom piece? 12. So the radius will be f of x minus 12. You're again doing big minus small. All right, so you have f of x here, you have 12 here. If you subtract them, you are left with this little bit up here. So now we can simply do our integral of pi times the radius squared dx. So that will be f of x minus 12. Now from where to where for the units? Well, the region starts here and ends here. So where are we starting? It looks like 2. Let's make sure that's actually correct. If I plug in 2, you get 16 minus 4, which is 12. So that looks good. And then we end here at 6. 6 times 8 is 48 minus 36. That is also 12. So we are going from 2 to 6. And that is the integral that will give us our answer. So let's plug that into the calculator and see what we actually get. For this one, it's a little bit more complicated. I would recommend typing the equation in. 8x minus x squared. And then when you type this in with the integral, you can actually use the f of x. So the integral from 2 to 6 of pi, make sure you hit the times, parentheses, f1 at x, go out of the f parentheses, minus 12, and then don't forget to square it after the parentheses, and dx. Hit enter and you get 107,233 is our volume. Alright, so that is one way a different axis can look, but it can also look slightly differently than that. Here I've got a very similar graph, same equation, but this time that blue line we're going to rotate around is above it. And that changes things just a little bit. So if we rotate around this way, it gets a little weird. What does this shape look like? Again, I'm going to try to convince you it doesn't matter what the shape looks like. This blue line is the center of your cross section, so just draw a half circle from there to the function. Okay, will it go to the other side? Yes, it will wrap around, but we really don't need to know too much about the other side. All the numbers we need are going to be over here. So that is the radius. So how can I make a mathematical statement to describe that red line? Well, the distance from here to here is f. The distance from the bottom to the top is 20. So if I want the amount between them, I subtract big minus small. So the radius is going to equal 20 minus f of x. I'm hoping you're seeing that big minus small is a big theme here. To get the radius over here, we took the big one and we subtracted the small one. Same thing here, we're taking the big value and subtracting the smaller value. Our integral is going to be very similar because the graph is basically the same. The integral from 2 to 6 of pi, our radius now is 20 minus f of x squared dx. So type that into the calculator and that'll give us our next answer. I'm going to have to erase a few things here. Here, I'll erase this over on this side and move the calculator over. There we go. So I need the integral from 2 to 6 of pi, don't forget the times, 20 minus f1 at x, and then move out to the correct parenthesis and square it. So make sure you're squaring the whole thing, not just f1. Getting your parentheses straight is very important. dx, hit enter, and you've got your answer, 375.315. Alright, so most of these you're not going to do by hand because the integral will be fairly complicated. So you want to make sure you have an idea of how to type the integral into the calculator. And again, remember the radius is very often big minus small.